How many stages does a rocket need?
Right, so last time our rocket had initial mass m0 that was composed of useful mass, i.e. mass of a satellite, useful mass, plus structural mass, so the body of the rocket, and the mass of the fuel. And as time goes on, our mass changes, but of course only this quantity changes, the fuel, because the rest is solid. But now we allow our rocket to have stages, so actually the structural mass will also decrease in a discrete manner. But this is going to happen in this video. But in the last video, we understood that the speed of the rocket is given by the following equation. So this is speed at time t with initial velocity equal to 0. And u was ejection speed, ejection of particles or fuel. So now let us consider stages. And to have a concrete example, suppose we have 3 stages and we write m0, our initial mass, as m useful plus m1 plus m2 plus m3, where m1, m2, and m3 are the masses of these stages. Well, and mu is contained, is probably attached to the third stage, but that doesn't matter. And what we are going to assume is that each mi is obviously composed of 2 things. First of all is the structural mass of that stage plus the fuel stage, the fuel mass that is contained inside that stage. So we will assume that this structural mass is equal to lambda mi, and then because they sum to mi, the fuel mass is thus going to be 1 minus lambda mi. When the first stage becomes empty, our rocket will attain a speed of v1, and this is going to be equal to u of ln m0 over m useful plus lambda m1 plus m2 plus m3, right? Because the only mass that we have lost is the fuel mass of the first stage, which is 1 minus lambda m1. So this will not take part in this equation. So then what we assume is that the first stage separates, so this lambda m1 disappears. So then mass becomes mu plus m2 plus m3, and we assume it happens instantaneously, and we keep flying. So then when when a fuel is when the fuel ends up in the second stage, we reach our next speed, which is going to be, so when the second stage becomes empty, we reach speed v2, which is obviously going to be v1 plus u of ln our initial mass for the second stage, which is this, mu plus m2 plus m3, divided by m useful plus lambda m2 plus m3. Again, because the only mass that we have used up is the fuel from the second stage. But v1, here it is, we have an expression for it, can be put here, and then u can be taken outside, and then we can just use the addition law for logarithms to get that v2 is actually u of ln m naught over mu plus m3, so this fraction, times mu plus m2 plus m3, mu plus lambda m2 plus m3. Now, as a small exercise for you, I want you to check that after the third stage will use up all of its fuel, we will get this final velocity of u times ln and the product of these three fractions. So now I suggest we slightly rewrite our expression by introducing the following variables. Alpha 1 is m naught over m useful plus m2 plus m3. Alpha 2 is mu plus m2 plus m3 over mu plus m3. So I'm kind of following these fractions, except I do not add this lambda term. And then alpha 3 is mu plus m3 over mu. And then you can actually see that this expression becomes this, alpha 1 or 1 plus lambda alpha 1 minus 1 times alpha 2, 1 plus lambda alpha 2 minus 1 times alpha 3, 1 plus lambda alpha 3 minus 1. So this is nice because now you can see that these three terms, these multiples, are symmetric. So if we replace alpha 1 and alpha 2 with alpha 3 or whatever, then the total value of this multiple will not change. So the question is, when is this maximized? When is this maximized? Turns out that it is actually maximized when alpha 1 is equal to alpha 2 and is equal to alpha 3. If you want to see it and prove it, which I really suggest you do, use the following fact. X over 1 plus lambda x minus 1 is monotone increasing. And remember that lambda, the modulus of lambda, is strictly less than 1, due to our model. So then you will have a product of three similar functions that are monotone increasing. And another thing to keep in mind is that alpha 1, alpha 2, and alpha 3 are not independent variables, and if you want to increase one of them, you will have to decrease another one of them. So this condition is kind of intuitive. So when these three quantities are the same and equal to some number alpha, we can solve this equation and get that alpha is 1 minus lambda over e to the minus our final third velocity over 3u minus lambda. Right now, one can observe that the product of these alphas is actually just the ratio of our initial mass to the useful mass. And using the formula above, this can be just rewritten as 1 minus lambda cubed over e to the v minus v3 or 3u minus lambda cubed. So this equation has everything now. We have our masses, we have our parameter lambda, and we have the speed that we can set if we want to reach the orbit. Now, we did our calculation for three-stage rocket, but generally for n stages, the result is just the same with a different exponent. We will have that mu, m naught, over useful mass is 1 minus lambda e to the minus v3 over nu minus lambda all to the power n. So now we have a general formula for n stages, and we can see how this ratio changes as we variate n from 2 to 3 and 4 and so on. Sorry, so in the previous formula, this was of course the n, because it's the speed attained at the nth stage. So for real-world calculation, we want to take Vn to be, say, 10.5 if you want to send something to the moon. So go to the moon, because you would then have to break away from Earth's gravitation, and you can show that the speed has to be around 10.5 kilometers per second for that. We also take lambda to be 0.1, which is a realistic engineering constraint that we have discussed in the previous video. So for every unit of structural mass, you would have around 10 units of fuel. And then remember that ejection speed for us was 3 kilometers per second. So now you can stop the video and calculate this number for n equals 2 and n equals 3. So for n equals 2, I get this number to be 149. For n equals 3, it becomes 77. And for n equals 4, we get 65. So what does it mean? It means that in this case, the total mass is around 149 of that of useful mass. Here it's 77, and here it's 65. So let us interpret these results. For every ton or any kilogram of useful mass that we actually want to deliver to the orbit or to outer space, you need 149 units of the total mass. So actually the rocket needs to be quite heavy for 1 unit of useful mass, whilst for 3 stages this number drops dramatically. So if you want to send 1 ton of useful mass here, you only need 77 tons of total weight in your initial rocket. And then you see that if we have 4 stages, then it drops even further, but the difference is not that drastic. So actually, n equals 3 appears to be the most profitable solution, because if you increase the number of stages, this will make the structure of the rocket more complex. But if you only allow yourself to have 2 stages, i.e. only once your rocket will lose some of its structure, you will waste a lot of energy bringing useful mass up. So n equals 3 appears as the most optimal solution, and this is what you actually see in reality. If you look at any rockets that go to space now or used to go to space back in the days, you would notice that all of them were 3-staged. But now you have a mathematical background for why is this the case? Why is this the most optimal solution? So now a small puzzle for you. Suppose we are in the ideal situation and we allow an infinite number of stages. So in some sense, our rocket becomes a candle that burns and loses all of its molten part instantaneously. So so what you can demonstrate is that if you allow an infinite number of stages, then you can reach any speed you want.